one more fundamental and very scoring chapter, photochemistry. Before that, just I will have a short discussion about the Jablonski diagram. What happened if a molecule is excited? Let's say you have a molecule. If it is excited with some radiations or some light, the molecule go to the excited state. Then what happened in the excited state? Let us understand. Let us. This is a single ground state of a molecule, and in a single state, there will be multiple vibration level. Let's say it is V is equal to 0, V is equal to 1, 2, 3, 4, etc. And this is the first excited state, S1. So S1 will contain also multiple vibration level. So this is S1, this is V is equal to 0, V is equal to 1, 2, 3, 4, and it is S2. And similarly, S2 will have different vibrational state. What happened? This is the energy. So if let's say one molecule is here, this is M, we have excited the molecule by some, let's say, some energy. The molecule is going to excite into the higher level, energy level, based on the energy what we provide. So basically, the molecule is going to excite in the state of S2. Then we will understand what's the phenomenon that happens here before doing the exact photochemical reactions. So after reaching S2, what will be the fate of the molecules? So what happens? The molecule can come back to S1, that is called IC. IC means intersystem crossing. Crossing. If the question is asked like what is the phenomenon happens in the excited state, then let's say after intersystem crossing, sorry, internal conversions. IC means internal conversions. This is internal conversions. I should erase basically this wrong word. This is internal conversions. Internal conversion. Let's say because of internal conversion, the molecule reaches here. The molecule come down to S1. Then from S1, the molecules come down to V is equal to 0. That is, the process is called vibrational relaxation. Relaxations. Vibrational relaxations. Couple of minutes, you will just seems as physical chemistry. You may wonder why Sir is telling that. Now, when I will discuss the organic chemistry, then you will understand why I emphasized on this topic. Now, from S1, not S1, V is equal to 0 of S1 is come back to the S0. Different vibrational level of S0. Let's say it can come V is equal to 0, it can come V is equal to 2. That phenomenon is called fluorescence. Fluorescence. So if it is asked from which state fluorescence occurs, fluorescence always occurs from fluorescence always occurs from we should always keep in mind V is equal to 0 of S is equal to 1. First excited state and the vibrationally ground state. V is equal to 0, S is equal to 1. This is the source of fluorescence. The molecule comes back in a radiative way. We must emphasize the radiative way. If the molecules come back in a radiative way to V is equal to different another vibration level of S is equal to 0. Where it will come back, it is not restricted, but it will always come back from this state. That's the origin of that's the state where the fluorescence phenomenon occurs. So this is radiative. Always we should keep in mind radiative. Then what are the process that is associated for a molecule to come back to V is equal to 0 p 1? The process 1 is IC, internal conversions. After internal conversion, through vibrational relaxation, the molecule come back to V is equal to 0. IC plus vibrational relaxation. Tonal relaxation. And this phenomenon from singlet to singlet. Singlet to singlet means in bracket S1 to S0. Again, I am telling we are doing fundamental discussions. If we have fundamental concept clear, you can practice a lot of examples at your home. But provided our basics should be crystal like clear. Now, why we are telling like that? The excited state phenomenon that is involved in photochemistry always, sometimes not always, happens in this state. That's why you have to take care about this state. The reaction that we are going to discuss that happen in this state. That's why we are discussing this Jablonski diagram. After what happened, the molecule sometime, let's say this is the triplet state T1. The molecule can come from S1 state to this T1 state. Why? Intersystem crossing. Intersystem crossing. ISC. So now the molecule is triplet state. Then from triplet state, the molecule again come back to different vibration level. Let's say this is V is equal to 0, 1, 2, 3, 4, etc. And then this is S is equal to 0 again ground state. V is equal to 0, 1, 2, 3, 4, etc. The molecule again by vibration relaxations comes here, and from here to here, if it comes back to different state by radiative, then we are going to mention a term is at phosphorescence. Phosphorescence. Okay. So the excited state reaction in photochemistry happens is in S1 and T1. So what type of information I got it from these discussions? Number one, depending upon the energy initially applied on the molecule, it can go to S2, it can go to S3, S5, whatever. It upon your choice, upon which amount of energy you're going to excite. But where it goes by intersect by ice, it will come back to S1. From S1 means by ice it can come from V is equal to 2 of S1, V is equal to 3 of S1, but from V is equal to 3 or 4, it will come down to V is equal to 0 of S1, that is called vibrational relaxations. So from V is equal to 0, then from this state, the fluorescence takes place. And by intersystem crossing, it can go to the triplet state, and from there also similar way, it will come back to phosphorescence. Here, the molecule has more lifetime. More lifetime means the molecules spend some more times than that of the single state here. So S1 has quite less lifetime. Now the question comes from in which state the photochemical reactions take place, on which excited state That's the first basic MCQ. We could not cover this MCQ until unless we have this kind of discussion. On which state photochemical reaction take place? The option is it can take place in single state also, it can take place in triplet state also, or it can take in both place also. Okay. So now after this discussion, we can later will give some example. It can take place on singlet state means always S1. It can take place in triplet state. It can take place in singlet plus triplet. So this is the perfect answer. So this is the main basics of photochemistry. Now we'll try to see some examples that what happens. So now up to that we understand now in both the states sometimes the reaction can take place on S1 only S1 photochemical reaction. It can take place only S2 sorry T1 triple state 1 and X can take place on S1 plus T1 and both states simultaneously. The details of these things we will understand or read in physical chemistry. That much we need for our discussions. Now we'll move to the important one photochemistry of carbonyl compounds. Photochemistry of carbonyl compounds. Carbonyl compounds. Compounds. So what happens? Let's say we have a where the first point will come where the photochemical reaction carbonyl compound takes place. It can be in singlet, just to understand. It can be on triplet. It can be on both the state S1 and T1 simultaneously. Let us try to understand what happens. So this is the carbonyl compound in ground state. We have excited these carbonyl compounds by some energy. Now the molecule is going to excite dot and dot. So this is the excited state. Here the reaction takes place. So there are mainly I will discuss about the two categories. One is alpha cleavage or Norrish type 1. Routinely the question is asked from this chemistry. Norrish type 1, beta cleavage or Norrish type 2. There are some more classification that we will discuss. So mainly alpha cleavage and for that is termed as Norrish type 1, beta cleavage that is termed as Norrish type 2. Now we'll on details we'll see. Today we'll discuss about restricted discussion on Norrish type 1 and type 2. Next day we'll discuss photochemical rearrangement. Almost 6 to 7 or 8 marks is asked from this chapter. That is easily can be done. So scoring from reagent chemistry is quite tough, but scoring from this chapter that I discussed in last couple of months, like stereochemistry, spectroscopy, photochemistry, these are easy scoring chapter. That's why I'm covering this chapter uh, initially. Okay, so Norwich type 1. What happens here? Let's say we have a carbonyl compounds R C double bond O. Sorry, just I have to put one more bond. Maybe you have read this example, but yet I am discussing from the beginning. Slowly I will take you to some different interesting examples. R CH2 C double bond O, then C we have another R dash here, and CH2 R double dash. This is the molecules. Initially, what happens when we excite the molecules? Then this bond clips and produce one acyl radical on alkyl radical. This is termed as primary process. This is primary process. In the first step, what happened? This bond, so this is definitely alpha. So this alpha R CH2 C double bond dot plus CH dot CH2 R dashed. So this is the step one. In the second step, what happened? That is called secondary process. The first process is the generation of a acyl radical and one alkyl radical. Here, the question is asked. You have a look on the question. They asked that they simply say about the process, and they asked which type of mechanism is this? Is Norrish type one, or in which type of categories? Type one or type two? If we look that, if we can identify that from the product, that there is a cleavage of carbonyl and C alpha bond. This is alpha atom, alpha carbon atom. That is going to be a Norris type 1. Then in the secondary process, next process, what happens? Secondary process. This carbonylation takes place. Okay. Means this RCH2 C double bond O dot again undergo this kind of cleavage and produce R CH2 dot plus 1 carbon monoxide. This is called decarbonylations. Decarbonylations. So if the question is asked, MCQ is asked. Now a question is always asked for fundamental point. So decarbonylation takes place at which process? Means which stage? It happens on secondary stage. It is a secondary process. Then what happens? We have this RCH2, this RCH2, RCH2 dot plus again this RCH2 dot R. They make a bond, forms RCH2, RCH2, R. Again, this RCH2 dot, we have another alkyl radical, that is CH dot CH2 R double dot and R dashed. Again, they make a bond R CH2 CH R CH2 R double dot. So that is called recombination. Recombination. So the secondary process composed of decarbonylations plus recombinations plus we'll see some more there. So just analyzing the product, you have to understand the where the initial cleavage happened in primary process. We'll be given some products. We have to analyze the product. Then we have to take conclusion in primary process which bond was responsible for that. So now we identify two process. One is decarbonylations, two is recombinations. Number three we'll see. But number three is intramolecular hydrogen abstraction. Intramolecular H abstractions. Hydrogen abstraction. Hydrogen atom abstractions. Abstractions. Just ABS. How it will happen? We know that initially we had this acyl radical, and we know that we had these fragmentations R dash CH dot CH2 R double dot. This is alpha and this was beta. Then abstraction of H dot, it occurred from this C beta atom. Then what will be the product? R, we will have different new aldehyde plus R. Now once the proton, not proton, H dot removes from beta to this acyl radical, it will be like that. R double dot. Basically it's nothing but these compounds. R, CH, double bond, CH, R dash. So we have got one alkene. What I'm trying to do, just taking one general examples, we're trying to show the all the possibilities involved in secondary process of Norrish type 1. So we got initially what we got? We have got two alkane by recombinations, two alkane, two new alkane by recombination. We have got carbon monoxides by decarbonizations. Let's say put on star. We have got new aldehyde, and new alkene by intermolecular molecular abstractions. Then what will happen on intramolecular proton abstraction? Intramolecular hydrogen abstraction. I should not say proton, hydrogen atom abstractions. Now, if we know the every details about Norrish type 1 process, then perfectly we can answer on MCQ. So, what the process that is involved in the secondary processes of Norrish type 1? Number one, decarbonylations. Number two, recombination. Number 3, intramolecular hydrogen transfer. Number 4, this is intermolecular, not intermolecular. Intermolecular hydrogen atom transfer. Number 4, intramolecular hydrogen atom transfer. Okay, this four process is here. Then what will happen if this is intramolecular transfer? Intramolecular. We have this O. Sorry for wrong structure. This is dot plus r dash ch dot ch2 and r double dot. This is alpha. This is beta. What will happen from here? I am again drawing it for our understanding. CH and let's understand CH2 double bond O dot. This H dot is going to transfer here. So as a result, what we are going to get? C R CH dot C double bond O dot plus here one alkane RCH2 CH2 R double dot. So it is nothing but R, a new bond will form between this and this using two electrons. This is a ketene. So the products that we got after Norrish type 1 fragmentation is this is 1 carbonyl, new alkanes, number 3 new aldehyde, number 4 alkene, number 5 very much interested ketene. If you can identify one ketene product, that is because of Norrish type 1. This is one, this is point 1, output 1 from our discussions, and output 2, that is the process involved in Norrish type 1 in secondary process. So here I am not going to write, we know the number 1, so it is the decarbonization, number 2 recombinations, number 3 intermolecular H abstractions, number 4 intramolecular. So these things fundamentally understand, and is some basic question is asked on a written statement, in not in terms of structure, written statement, then we can answer this also. And because of very short time, there are a lot of things that also can be discussed, but I will also tell that you should remember some points for the sake of exam. Later we can answer all the things, or you can have a read the books and you can understand, but for being time we cannot discuss it. I'll tell to understand this. So then you can ask, just I am not supposed to discuss this, but second discuss for the sake of understanding. If it is asked, are there any proof that this kind of alpha cleavage happens? Proof of alpha cleavage. Let's say we have this carbonyl C6H5 CH2 C double bond O CH2 C6H5. So it is going to cleave at, let's say here, after H new C6H5 CH2 C double bond O dot and CH2 C6H5 dot. Now we can trap these two radicals. Let's say we used this molecule. This is a radical trapper. It can trap the radical O dot. Okay, then this will make a bond with this. So one new bond will find C6H5 CH2 C double bond O, these were big molecules, and plus also with this one also NO CH2 C6H5. This indicates that yes, definitely there is a radical formation. So radical can be trapped by this molecule. So if the question is asked which of the following molecules can be used to trap a radical, then this will be the answer. So now you understand that it happens. Now we take a real example. What is going to be? The first one will come if it is a symmetrical alkene, then we don't have any problem. For symmetrical alkene, we don't have, let's say it's a symmetrical alkene, carbonyl. We don't have any problem. It will be clipped like here it clips, whatever. It is going to produce the same thing. But if the alkene is unsymmetrical, then what's the problem? So for the case of an unsymmetrical alkene, unsymmetrical carbonyl. Let's say we have this carbonyl C C double bond O CH2 CH2 CH3. So H nu and H nu. Let us consider here it is cleaving these bonds. So then we will have this acyl plus CH2 CH2 CH3. This alkyl. And let's understand it's, let's say it's a cleave these bonds. So this is basically cleave of these things, and here it cleaves this bond. And here I put the sign. Just it's a, just don't be confused that let's say I am not supposed to show this in this way. It's A that is going to cleave, and it's a B which is going to cleave here. Let's say B. Then it cleaves this one. We will have dot plus C double bond O dot CH2 CH2C. Then which is the possible path, A or B? The answer is that formation of a stable alkyl radical. Formation of a relatively stable alkyl radical. For this process A, we got a primary radical, 1 degree radical, alkyl radical. Here we have got a 3 degree alkyl radical, And we know that the stability of 3-degree alkyl radical is more than the 1-degree alkyl radical. As a result, it will go through this pathway. So this is the right pathway of cleaving. This is the wrong pathway of cleaving. So this will be produced. We should remember for unsymmetrical carbonyl. Then the process what I told that will be. We'll take some different complex example now.